This is a short video about part of 4.1 in Stein's elementary number theory book, and it's about the statement of the quadratic reciprocity law. And what we're going to focus on in this video is just what is a quadratic residue. So before we talk about this famous reciprocity law, let's get a handle on some of the other vocabulary that we need to be comfortable with. So a quadratic residue, what we're going to do is we're going to fix a prime number p. If we pick an integer a that's not divisible by p, then we'll say that this number a is a quadratic residue mod p if a is a square mod p. Otherwise, we're going to say a is a quadratic non-residue. To get an idea of what is this, let's look at a concrete example. Let's look at what are the squares mod 5. So when you square the elements of z mod 5z or z5, whatever you want to call it, when I look at squaring those elements, what are the squares that I get? So if I start with, in our case here, 1 would be the first thing, since I want to just stick to integers that are not divisible by p, so 0 is divisible by p, so we don't include that. So if I square 1, I get 1. So what should this say? What do I want you to focus on? Make this a little thicker. 1 is a quadratic residue, mod p, because 1 occurs as a square. So that 1 there is a square. What else do I see? When I square 2, the next element, I get 4. So 4 is also a quadratic residue mod p. What else? When I square the next element 3, I just get 4 again. So again, nothing new. I already knew 4 was a quadratic residue. And I see when I square 4, kind of the last element of z5, that's not divisible by 5, I get 1. So if you look at the things that I've highlighted for us again, what are the quadratic residues mod 5? There's 2 of them, 1 and 4. That means that the other numbers in z5 that I've not highlighted, namely 2 and 3, those would be the quadratic non-residues. So the non-residues would be 2 and 3. So 2 and 3 are non-residues. I'm trying to highlight a lot of good stuff here. And 1 and 4 are both the residues. So when it's tricky, right, you're looking for when is the output a square, right? So that output that is the square, that thing is what we're calling the quadratic residue. Maybe it would be helpful if we did one more, if we tried to figure out maybe something small. What are the quadratic residues mod 3? Is that easy to do? So if I look at 1 squared and 2 squared, what do I get? I just get 1, and in this case, when I do 2 squared but reduce it mod 3, I just get 1 again. So mod 3, 1 is a quadratic residue, whereas 2 would not be a quadratic residue. So 1 is quadratic residue mod 3, but 2 is a quadratic non-residue mod 3. Just kind of shorthand some stuff. Hope it makes sense how that works, right? Again, 1 was the only thing that showed up as a square. Okay, so there is a computational symbol that helps us figure out if a given integer is a quadratic residue mod p. And it's called the Legendre symbol. So here's the definition of it here. We're going to look at an odd prime p. We'll talk about what to do when p is 2 later on. 2 is the only even prime. So let's focus on odd primes for right now. So if p is an odd prime, let's just let a be any other integer. Who cares? So what we're going to do is the following. Here's the notation for it. So don't focus on the piecewise stuff to the right. The notation for the Legendre symbol is this, parentheses a over p. And when I see that, what I usually say to myself is that's the Legendre symbol of a mod p. So again, to say that one more time, the Legendre symbol of a mod p. Now here is what this symbol is defined to be. It's defined to be one of the following 3 possibilities. That symbol represents 0 if p divides a. It represents positive 1 if a is a quadratic residue mod p. And it represents negative 1 if a is a quadratic non-residue. So in our examples above here, let's go back to what we've highlighted. What should I expect? I expect that the purples, right, 1 and 4, those were quadratic residues. That means that when I plug in 1 for a and 4 for a, notice what you get. You get a positive 1. And so what does that positive 1 represent again? That particular a, the 1 and the 4, were quadratic residues. On the other hand, what did we do above? We saw that 2 and 3, they were not squares mod 5. So when I plug in 2 or 3 for a, Since they're not squares mod 5, they're quadratic non-residues, and so the Legendre symbol would be -1. So as soon as you see a Legendre symbol of -1, that tells you right away, oh, that A is not a square mod 5. 2 is not a square mod 5. 3 is not a square mod 5. And the last one here, maybe I should do this one right here. That's what we just got finished doing. And then the last one, what if you plugged in just 5 itself? Well, 5, the Legendre symbol of 5 mod 5 would be 0. Well, because the GCD of 5 and 5 is definitely not 1. It's 5. That's why it's 0. So the Legendre symbol, we'll look at, right now, it's kind of hard to compute by hand. Right now, your only way to compute a Legendre symbol is to just make a list of what are the squares mod 5. Now, like 5 was an easy number to do because it's small, but like, what do I do for the Legendre symbol if P is, something like, I don't know, 101 or something that's not prime, like 97. Like, that's not even that big, but I definitely don't want to do it by hand. So what we'll look at in this section is there are some properties that the Legendre symbol has that will make these computations doable by hand. And you could probably guess that these things have been around since like the 1800s because Gauss used this stuff in order to talk about his famous quadratic reciprocity law, which again we're aiming towards here. So we are going to develop some techniques to compute the Legendre symbol by hand, but if it seems a little bit abstract, that's a good thing because right now, or that's natural, that's normal, because right now the only tool we have is to just list out what are all the possible squares and kind of do it by exhaustion. Or we could use Sage. So Sage has a built-in function specifically to compute the Legendre symbol. And it's exactly what you probably think it was. Maybe you didn't think of the underscore, but there it is. It's just Legendre symbol, Legendre underscore symbol. So that command computes the Legendre symbol in Sage. So to give you a picture of what it looks like, what would you do? Something like this here. This asks, is 2 a square mod 3? This is asking Sage the question, is 2 a square mod 3? And what does Sage say? When the Legendre symbol is -1, what do you have to know? You have to know how to interpret that. Well, that's just right here. Look where -1 is. That says no, it is not a square mod 3. It says that 2 is a quadratic non-residue mod 3. Cool. If we look at another one, and I think we did this by hand too earlier, right? What if you took the Legendre symbol of 1 mod 3, then yeah, 1's definitely a square. And look, I get the Legendre symbol is 1, and remember, anytime the Legendre symbol is 1, that indicates that this A right here is a square modulo P. And let's see, what else do I want to say about this part here? Maybe the last one is the only one that looks a little bit goofy. There's a difference between the element 3, the integer 3, and the thing mod 3, 5, right? This is like the equivalence class of 3 mod 5. So some books write it that way, or maybe some books write it 3 plus 5z. Any way you want to write it. The point though is, what we saw earlier was, and it's actually right above here, 3 is not a square mod 5. So the Legendre symbol is -1. And what that also tells me then is anything equivalent to 3 mod 5, that's how you should think of that. Anything equivalent to 3 mod 5 is also going to have a Legendre symbol of -1. And to say that just one more time, the Legendre symbol of A mod P, again, it only depends on what is A mod P. So what we can do is we can talk about the Legendre symbol of A mod P for elements of Z mod PZ, right? So like these equivalence classes. The Legendre symbol of A mod P, when A is an equivalence class, it should be the same thing as the Legendre symbol of the integer, say A tilde P, where A tilde is any lift of A. So what do I mean by that? What are some of the lifts of 3 plus 5z, if I want to denote that equivalence class that way? Well, some of the lists of 3 mod 5z would be something like 3. 3 is a good lift of that. But then so it's something like 8. 8's a lift. And so it's something like, if I had 5 more, can I do that? 13. What I'm saying to you is if you plugged in 8 or 13 into the Legendre symbol, mod 5, you should also get the same answer. It should be -1. So the Legendre symbol respects these equivalence classes.